In this video, we're going to talk about stepper motors and how to control them using an H-bridge and Labview. So a stepper motor is an electrical motor that moves in discrete, precise, angular steps. So we basically have teeth and coils, and you energize a coil, and the teeth, which are either north or south pole of a magnet, are then attracted to the coil. So these allow us to do very precise, what we call open loop control. So we don't need to have some feedback loop, which makes it more complicated. We just energize the coil and we can get it to move. And another interesting thing about stepper motors is that if you keep the coil energized, it can hold its torque. Okay? The only problem with that, though, is you're energizing the coil, which does draw significant current and can overheat the motor if you try to hold it for too long. And so how it basically works is we have the two coils, we'll call them A and B, and you energize A and B both in a positive direction, and that'll like rotate your rotor. And then you energize A in the opposite direction, and that'll move the rotor the next step. Now, this is saying from 0 to 90 degrees. That's like if you just had like a cross. Typically, these motors will actually have multiple steps in them. But anyhow, so you energize A and B both in the positive direction. Then you flip A, but keep B in that direction. That'll move you more. And then you flip them both, and you just cycle through these steps. Now, there's a couple of different types of stepper motors. There's what's called a unipolar motor, which typically will have 5 wires, although it could have 6 or 8. And this has center tapped windings. I'll show those in a minute. And the nice thing about the unipolar is that you can just use simple transistors to drive these coils. You don't need a special H bridge. Okay. The downsides of unipolar is they typically are going to have lower torque because you're only using half of a winding, and they are less efficient. Okay, so simpler control, but lower torque and less efficiency. Now, bipolar can be done either with 4 wires or 8 wires. And so you don't have a center tap. Okay, but it does require a little more complicated control using an H bridge. And but you get higher torque because you're using the full winding, and you also have more efficiency. So let's take a look here. On the left, we have the unipolar. So we have 2 coils, and they have a center tap on each of them. So what would happen is in the 5-wire setup, you take the 2 common wires and connect those to ground. And then, so if you want to energize your coil positive, you put a high on the top, and then that goes to ground. So you just energize this half of the coil, which is why you don't have as much torque as you would if you were going to energize the entire coil. Likewise, when you if you look at the bipolar stepper motor here, this is a 4-winding one here. And so we're gonna energize this coil at the top, and then you get a full coil energized. But to switch the direction, you now have to put the positive on the other side. So you have to be able to flip the current on the entire coil. But if we look at the unipolar, if we put a high on the top, and then it'll be high to ground on the top half. And then we could put a high at the lower one, and then it'll be a positive to that, but that'll give us the negative or the inverse direction of current flow. So that's how we can flip the direction of the coil without the complicated H bridge. All right, now if we look at the 8-wire, we have the 8-wire stepper motor here. You have the you basically have the center tap coil, but it's actually separated. So by using an 8-wire bipolar stepper motor, you can wire it like this, the standard bipolar, the 4-wire bipolar over here, or you can wire these two separate coils in parallel. So like over here, if I just connected these center lines, then, but I energize the entire coil, I get the strength of the coil on here, and I just have my standard bipolar. So if I just wire these two together, I can end up with the 4-wire on the left. But I can also wire them in parallel, which is going to draw more current, but give me a stronger field. Okay, so here's this slide. I'm just talking about why we might want to use 8. So for the series, we can connect these in series, which would give us just an ordinary 4-wire. All right, and that gives you full inductance, so you get full torque at low speeds, less current because they're in series, so you get low speed, very high torque application. However, if we wire them in parallel, we lower the overall inductance, which will lower our torque, but we can get a faster response. So parallel connections are better for high-speed applications. And then again, if we connect the center wires, then we will simply be at the unipolar, which will have the easier control. And if you wanted to make a complicated controller, you could actually create one that could give you any of these wirings with it'd have to be a pretty complicated controller, but you could have all 3 of those at different times with the same motor. So that's the advantage of an 8-wire bipolar stepper motor. Now, so what is this H bridge? The problem with, as we said, the bipolar is that what we have to do is we have to reverse current in the coil. So here is a wiring. An H bridge basically requires 4 transistors. In this case, they're shown as MOSFETs. MOSFETs are usually more ideal to use for this than BJT type transistors, but you could use BJTs. But what you have here is you have 4 of these, but you only want to activate like Q1 and Q4 or Q2 and Q3. So let's take a look. We have Q1 and Q4 is on, so current is going to flow from left to right through our motor coil. And so that'll give us, call that a positive direction. And then we can activate Q3 and Q2, and that'll give us current flowing from right to left through the motor, so we can reverse the direction of the coil. So that's what they call an H bridge. So you have your H sort of shape here with the cross being where your motor is at. Now this can be used for an ordinary DC motor or a stepper motor. But the one thing you have to be very careful on this is this last case here where you turn on Q1 and Q2 at the same time, and or Q3 or Q4 at the same time. If you do that, you're buying a new controller because that one just shorted out and burn out your transistors. So you always need to make sure that you never get this case where the all of both transistors on the left or the right are on at the same time. Now, there's several different chips that are H-bridge driver chips. And again, the reason that we need this is the fact that our controller cannot output enough voltage or current to drive a motor. And so we need a separate driver. And they make lots of different sizes and types of drivers here. This is a integrated circuit, L293 H-bridge circuit. And so it actually has a standard H-bridge transistors that I just showed in the previous slide built into a single 16-bit chip. And so we can use this to drive either two separate DC motors or a stepper motor, which is what we're going to be using. And so the supply voltage for this can go all the way up to 36 volts. So you could have a motor, a 36 volt motor to power using this chip. And the logic is rated from 4.5 up to 7. So if you're using like a BeagleBone, you may have to actually add in a logic level increasement to get it up to like 5 volts logic to activate this. Now the output current of these are 600 milliamps per channel with 1.2 amp as a peak. So as long as you're not holding it constant, you can get above that 600 milliamp for short periods, but you can't hold it constant at more than that, or you're going to damage the chip. And now you can power this. They notice that they have channels 1 and 2, which will control one coil, and channels 3 and 4, which could control another coil. So again, those could be two separate DC motors or the two coils of a stepper motor. And there's enable pins, so you can enable them, and then you can put in the current as either a positive or a negative sort of input direction in there. So you have your inputs and your outputs to your 4 wires of your stepper motor, or your 4 yeah, so your stepper motor, even if you're using an 8 wire, right, you've got to do something with the other sides of those. So whether you connected them in series or parallel, those windings in there would connect. But now the enables then can be used if you want to do PWM type control of this. So you can just put a positive or put your positive or negative there and use the enable to pulse it back and forth. So enables are very handy for doing pulse width modulation, especially for a DC type motor, as opposed to a stepper motor. Now, if we're doing a stepper motor and we want to power our coil, okay, so this is like showing we're going to turn the enables high, and then we're going to put a low at A and a high at B, and that'll give us a forward current from A to B. And then the next step is to reverse that. So we just flip it high and low. And then if we want to basically lock the motor so it doesn't move, we can put in highs or lows on both. All right, now if we're going to wire this up to our USB 6009, right, we need to just choose our enable pins, and our phase direction pins. So we're just going to choose like P0, P0.0, P0.1, 2, or 3, like we used for the LEDs before. And then we'll decide whether to make them high or low as we showed on the other slide. Now, to run this through our Labview, we need to have our front panel controls, which will allow us, we want to be able to run the motor forward or backwards. We want to get it to step through those different steps. So we have a step sequence here, as I showed on the other slide: true, false, false, true, true, false. This is the stepper motor sequence to get it to move forward. Call that clockwise or whatever on your stepper motor, and to get it to move around. So we can do this using either like an array, and you can set up an array or basically a matrix and feed these 4 different values in, or we can use what's called a case structure. And now to make a full revolution, it depends exactly on which stepper motor you have. But like a lot of stepper motors, you have to do something like 200 steps or even 1,000 steps to make one complete revolution. So depending on your stepper motor, you'll have to determine what that is, either by the documentation or experimentation, and figure out how many steps it'll take to make one full revolution. So what I have over here is a control screen. So this here is a control screen for controlling a stepper motor. It's just a sample here. Notice we've got the bits here. We've got some LEDs just to show us whether those are moving or not. And then we have a direction. So we have a Boolean that can switch direction between either clockwise or counterclockwise direction. We have a timer to measure and control the speed of how fast the steps go. And one thing with stepper motors you have to be careful is if you make the steps too fast, the motor can't move that fast, and you'll actually lose track of where the motor is at. Now, to implement this, we chose to use the case method here. And so to use the case, we're going to use a case structure. The case structure is going to allow us to do either clockwise or counterclockwise. And then we're going to use what's called a flat sequence structure, which kind of looks like a movie screen, sort of the old movie reel sort of tapes here to show that it's like one frame after another. So let's take a look at this in Labview here. So here's Labview. And so what we have here are 4 sequences or frames. And so this is showing the true, false, false, true, true, false, true, false, true, true, false, true, true, false, and so on. So I have my 4 steps here, which give me one complete sequence of steps for the motor. And then we have the timer here running these. Well, we're going from frame 1, 2, 3, 4 in there, and this will go in the clockwise direction. Now, so I put all these in here, and we're outputting to our DAC. Though, just like we did before here, we have a Booleans to Boolean array, and it's going to step through this sequence. Now, notice right here, though, this says true. So this is our case statement that allows us to choose either clockwise is true or clockwise is not true. Clockwise is false, which would mean counterclockwise. So if I click this, you'll see these move. So there's they're kind of like one behind the other. So when you flip your case to false, you see I have the same thing, but the order of these are different. Now, again, we could have done this with an array, but this is just illustrating it using a case statement and then this sequential method here. So these are basically the same steps we had before, but in reverse order so that the motor will return in the reverse direction, so the counterclockwise direction. So that's using the case statement. So I have the case statement here, and inside of the case statement, I have my four flat sequence statements. And then outside of that, then, well, feeding the case structure is my flip switch for clockwise or counterclockwise, true or false. And that's connected, you see that's connected right to this rail here of my case statement. And then, of course, we have a while loop, which is going to count how many iterations that you want it to go around. So again, depending on if you want it to make like one complete rotation, you need to find out, okay, how many revolutions or how many steps does it take to make one full revolution? And so it could be 200 steps to make one full revolution, or it could be more or less, depending on which stepper motor that you actually have. All right. So, but that just kind of gives us this here. So we talked about the different types of motor wiring for our stepper motor. We talked about what the H bridge is, and we talked a little bit about how to program this using Labview.